Okay, so chapter 5 and Markov chains. So the whole idea of a Markov chain is we're going to model a process where the probability of the next event, so we've got events occurring in time, and the probability of the next event will only depend on where we are now, not the sort of the past history of how we came to get to this point. So it's what we call memoryless. We're saying that it's a key idea. I'm in a state at this particular point, and the probability of jumping to the next state only depends on where I am now, not how I got to this point. So we don't have any sort of history. So this is a whole part of what we call a random process. And a random process is we're going to have some random variable, xn, and n is going to be indicated by some sort of set t. But in this case, we're going to make it nice and easy. We're going to talk about discrete time. So t basically takes time points. So we have time point 0, 1, 2, 3. So they're just going to go across in a discrete time. We're also going to make it nice and easy. So the xn could be continuous random variable or discrete random variable. We're just going to have a discrete random variable. So it's going to have a countable state space. So you basically, your s, your possible states, could be x0, x1, all the way up to xn. So let's put this all together. We've got our xn, n, which indicates each of these variables is just going to be a natural number. So you'll have 0, 1, 2. So you got the value at time 0, time 1, time 2, time 3. And at each of these points, x can take a value of discrete states. And the key property is this: the probability that the state at time n, given at time 0 we had a state of x0, and time 1 we had a state of x1, all the way up to xn minus 1 we had a state of xn minus 1. That can be collapsed down to just this simple one, that the probability that I'm in state s at the nth time point is only dependent, it only depends, is conditional on the state at the n minus 1 time point. So basically all this information that we had up to here disappears, and all we care about is this, the state, the last state I was in. Now, to make it even easier, what we're going to do is, because the state space is just a discrete set of sets, instead of having all of them, we're just going to label these states as 0, 1, 2, etc. So it's just nice, easy. So the states could be raining, not raining. We'll have one later where it's vending, not vending. Instead, we're just going to call that sort of 0, 1, 2, just to make it nice and easy. The other thing we're going to consider in this is what we call time-homogeneous Markov chains. So what does that mean? Basically, let's say I was in state I at time n. So this says I was state I at time n. And we now make a jump. We say, what's the probability I'm in state j at time n plus 1, given I was in state I at time n? That probability is going to be exactly the same as if I went right back to the start and said, what's the probability I'm in state j at time 1, given I was in state I at time 0? So the thing is that all we really care about is the next step. We don't say, oh, I've been going for 20 times or 30 times or 40 times. The probability of going from state I to state j in a single step is the same whatever time I look at it. And to make that nice and easy, we will just call that Pij, which is the probability of going from state I to state j in a single time step. If you don't have that property, we call it time inhomogeneous. And if you do have the property, we call it time homogeneous. So let's look at some examples. The first one we're going to do is we're going to have a coin and we're going to toss it. And it has a probability P of getting ahead. And we're going to count the number of heads. So we're going to start with 0 heads. And then every time I toss it and get ahead, we just go up the state. So the state is the total number of heads I've got so far. And we can describe this in what we call a state transition diagram. So state transition diagram, in the circles we have the states. So here's the starting point, I've got no heads. And then we keep going, and I can, with probability P, go up to state 1. Or with probability 1 minus P, just keep staying this. So this is where I just keep tossing tails, and then I top ahead, and then I go up to state 1. Now again, I could keep tossing tails, but then eventually I'd toss a head and go up to state 2. So you can see in this case, the arrows indicate changing between states, and the P gives me the probability of changing states. So this describes the setup of the process. Now, in reality, I might be going, if you actually looked at the values you got, it might go 0, 0, 0, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1, 1. So this is just describing how I move between the states. It doesn't actually tell me an individual process. So another one, we've got a vending machine, and the vending machine has 2 states. It's either working or not working. If the machine is working on any particular day, then the probability it will not be working is delta. So there's a delta probability that it will go from working to not working. And if it's not working, then we get a repairman in, and there's a probability of gamma that it's working the next day. So we're going to have, in this case, we have not working, and we will say that 0 is not working and 1 is working. So our state space is 0, 1. And here's our state diagram. This is it not working. This is it's working. If it's not working, there's a probability gamma of being working on the next day. If you're working, there's a probability delta of being not working. And obviously there's always the 1 minus delta of staying in the same state here, and the 1 minus gamma here. So here's we bounce between 0 and 1. The initial state, what do we do about the initial state, the x0? Well, either you might know it, you might say, well, I started looking at this vending machine and it was working, so you set it to 1. Or if you don't, you could basically choose a distribution. You could basically toss a coin to say which state am I in. And if we assume the machine, in this case, starts at state 0, so it's not working, we can then say, well, what's going to happen over this time? Well, if I start with 0, basically, I could stay with 0 with a probability of 1 minus alpha. So let's assume some values. Let's let gamma equal 0.2. So that's the probability if it's not working, it's working the next day. And delta has a probability of 0.9. That basically says if you're working, the probability of not working the next day. So you can see here that I could stay in the not working with probability 0.8. Or with probability 1, I can go up to working. What about the next one? Well, what's the probability that x2 equals 0? Well, you have to think about your paths. Basically, if you think about the tree diagram, you could have basically started working, then gone to not working, or stayed not working, stayed not working. With this one, we could have started with the gone to stayed not working, and then we started working, or we could have gone to working, stayed working. So I'll show you later how we get these numbers in a much nicer way. So just so we can see what this looks like, what I've got here is I've got some code that will simulate this. This will take a start state, how many days I want to simulate for, and we put in gamma and delta. First of all, our states we'll put in a big long vector, and we will set the first position that vector to the value that we start at. And then we count each day, and basically if we're not working, then we choose the probability in the next one using our 1 minus gamma gamma for either staying not working or going to the working. And if we are in the other state, which means that we're working, we can have our delta of going back. So let's run this. What I've done here is one of the chains, so this is 2 runs of that simulation. The first one I started in the working state. And what we've got here is this is the actual state each day of either not working or working. And you can see even up at this point, it's still bouncing backwards and forwards, but let's look at long-term behavior. I've worked out what proportion of the time I'm working. So you can see the state with 1, very quickly they start to steady out. They get this. They're sort of starting to, if we ran this long enough, they would basically have a steady state. We're going to spend a bit of time in this chapter looking at the steady states. This one started 0, it went up, and then it bounces, and then it settles down. So there's our starting notation, and we'll start to look at how we look at calculating probabilities of going from states to states over a certain amount of time next time. See you then.